Okay. Sorry for dilemma. Okay. So in the earlier lecture, we just take a brief idea about the sound wave, actually how sound wave travel and what is the basic parameters that related to sound wave. Okay, I hope the basic thing is crystal clear about the sound wave. What is rarefaction? When rarefaction is generated, what is compression? How the density will become maximum, then pressure will become maximum, and this type of localized area is known as the compression. If I am talking about the rarefaction, when the particles are moving apart, I am talking about those particles which are perform oscillations. When the particles are moving apart, then the density of a localized area will become lesser, and that particular localized area is known as the rarefaction. And the pulse that is moving with the speed of sound is known as the rarefaction pulse. Okay, beta. In the today's class, we just develop a relationship how we can write down the sound wave in the displacement form, and one another form we will also see how we can write down the sound wave in the pressure form. Here we establish the relationship between the displacement form and the pressure form. That is the first task of the today class. What is the second topics that we have to cover in today class? What is the speed of sound? How speed of sound that is very medium to medium? What is the formula of speed of sound? How many parameters in which speed of sound is depend? Okay. And after completion of the today class, we just able to analyze the some musical instrument such like as what is principle of organ pipe, how it is working, what is guitar, and in which principle it also working. Okay, so there are some types of basic understanding that we will take from the today class. Okay, beta. So let's move. Whatever I learned in the previous class, we also see in this slide. Okay. So first of all, I am discussing about what is the relationship between the displacement and wave and pressure wave. We already know that if we want to create a sound, we just required a source, and there are very popular source in the sound, that is tuning fork. Okay, we already discussed if we want to create a sound, we want a source, but here our source is tuning fork. Okay, so this is our tuning fork. Okay, so what happened, beta? We know that the in surrounding air is present, so we just focus in some specific volume of air, and that specific volume of air, that we can say that air column. Actually, we want to analyze what will happen when sound wave travels in the medium of air. So we just consider a small volume. First, we interested at this particular particle. So if we consider the air column having the cross-sectional area A, and suppose this point, if we consider this point that is at a distance x from a tuning fork, and if we create a wave from here, if we create a disturbance from tuning fork, the disturbance that move in longitudinal direction, we already know that. And the another part of this air column we consider here, say this point is B, this point is A. This is a small displacement, so we can say this distance is nothing but this distance is very, very small, beta, that is ds. That is ds. So if we want to ask you what is the initial volume of this air column, suppose this is the air column having a distance x, and the cross-sectional area A. So what is the initial volume, beta? We can say cross-sectional area into length, that is ADS. What will happen if we create a disturbance from air? The particle which lie at position X from the source, it start oscillating in this way, correct? So we can say that if the displacement of this particular particle which lie at distance x from source, that is ds, we can say this is s. This is s. Why s? Because we already know that if we want to write down the displacement form equation, the displacement form equation is written in form of s. So this displacement of particular particle of point A is S, that we show in this figure. Okay. At the same time, if you want to interested what is the displacement of the point that is at point B, so we can say this the particular point which lie at distance x, the distance or displacement or oscillation that perform it is S. And if we interested at the position of particle which is lie at s plus dx, so what is displacement of this particle? So we can say as it lie at distance x plus dx, then the same analogy we can say the distance or displacement that performed by this particle is s plus ds. S plus ds. Okay, sir. Then what will net final volume? So final volume, what is the net displacement? Suppose this is a particle A, this is a particle B. The particle A move S, the particle B move S plus ds. Then what is the net final volume? So we can say that our net final volume is nothing but dx plus ds. Dx plus ds. This is the net displacement and this is the cross-sectional area. So this is our final volume. So what is the change in volume? Why we interested in find out the change in volume? Because we want to find out why this wave is generated. So we know that this wave is generated because of the some pressure difference. So here we want to know what is the pressure difference. In air, which is a compressible fluid, if the pressure is come into picture, then definitely some change in volume will occur. If the pressure is come into picture, change in volume into come into picture, then the whole scene is created and the bulk modulus that is defined for a given material. So we can say that the air is a compressible fluid, and we know that the sound wave that is traveled due to pressure variation. So if there is pressure variation in space, if we choose some control volume and we study what is the change in volume. So this change in volume is nothing but V final minus V initial. Okay, that is ADS. So here, if we apply the formula of bulk modulus, that is nothing but excess pressure divided over volumetric strain. So how we can write down beta? What is change in pressure? That V dV upon V. So we can write down here what is the value of dV, that is ADS, and the volume, that is the original volume ADX. A and A will cancel out. Here the net excess pressure that is written as A minus B ds upon dx. This is very important formula, because this formula develop a relationship between excess pressure and displacement wave. Okay, sometimes the direct question asks what is the relationship between the excess pressure and the displacement wave. So here we can write down that our dP is the excess pressure, that is minus ds upon ds. Sometimes student will confuse what is dx. Dx is nothing but that is the length of that air column that I consider here. So what is ds, sir? ds is the displacement of that particular air column which having distance ds. Okay, beta. Let's move further next. we already know that the displacement equation is written as S equal to S naught sine omega t minus Ax plus phi. So as we develop a relationship between the displacement and pressure, so can we find out the pressure wave? Can we find out the equation of pressure wave? Why not? Why not? Because if we put the value of displacement in this equation, we will get value of pressure. But please take care of one thing here, how we can write down the partial differentiation. Here we know that the displacement is function of time and position also. So we have to careful whenever we want to write down the pressure equation. That's why we use partial differentiation sign here. Okay, so that we can mention with respect to which variable we want to find out the pressure. So here we want to calculate the pressure with respect to x. So if we put the value of s here, so we simply know that the differentiation of sine theta is nothing but cos theta. And here we can say this is constant value, that is the amplitude of displacement, and the coefficient of x is nothing but minus k. So if multiply by minus k with minus b, it will become positive. So this will equal to bks naught cos omega t minus ks plus phi. This is equation of pressure wave. So what is important point that we should remember from here, beta, that pressure wave, the amplitude of pressure wave is nothing but bks naught. bks naught. What is b? What is b, beta? What is b? So B is nothing but bulk modulus of medium. B is nothing but bulk modulus of medium. Okay, correct. Bulk modulus, whenever medium is given, we have to write down this is the bulk modulus. Okay, why bulk modulus come into picture? Because the medium having some elasticity property. Because medium, when pressure is vary, volume is vary, then bulk modulus come into picture for fluids. Okay, sir, no problem. Sir, what is K here? K is nothing but K is angular wave number. K is angular wave number. So how we can write down the angular wave number, beta? That angular wave number we already know 2 pi upon lambda. Okay, and S naught is the displacement amplitude. One more thing we should feel from this equation. This equation, what we can say from this equation, beta? If we want to this cos equation in the form of sine equation, how we can write down? We should add pi by 2 here. We should add pi by 2 here. So if we add pi by 2 here, what we will get, beta? If we add pi by 2 here, that sine 90 plus theta, this will become cos theta. So we can say that our pressure wave is bks naught, and this will can be write down sine omega t minus kx plus phi by 2. So what is conclusion from here? The conclusion from here is, if we see the equation of displacement, this is the phase of the displacement equation. If we see the equation of pressure, so we can see the extra term pi by 2 that come in the equation of pressure wave. It means pressure is 90 degree ahead of displacement wave. How we can see here, if we see if this is the phasor diagram of displacement wave, then pressure wave is like at an angle 90 degree ahead of displacement wave. This is the meaning of the phasor difference. That's why I can write down there, pressure wave is ahead 90 degree in phase by displacement wave. Direct question that can be asked from this point, what is pressure amplitude? We have to remember here, and we have to also know which one is ahead in phase. Okay, so on the basis of same concept, a question is given here. Please solve the given problem and comment about what is the answer. Okay, so you have 50 seconds to solve this problem. So here what is given beta? The equation of sound wave in air that is given in the displacement form. Bulk modulus is given here. We have to find out the pressure amplitude. Okay, sir. Here we know that what is equation of sound wave, that S equal to 10 micrometer into sine 500t minus 10x. So what is the equation of pressure wave? That we can earlier say that if we compare this equation with the standard equation, that can be written as S naught sine omega t minus kx plus phi. Phi is 0 here. So what is the equation of pressure wave? The pressure wave that can be written here, beta. If you want to write down the pressure wave, listen carefully. How we can say what is the pressure wave here? And we earlier said that the pressure wave that can be easily defined that B K S naught, and this can be written as sine omega t minus kx plus pi by 2. Okay. So what is the pressure amplitude? This is our pressure amplitude. So if you want to find out the pressure amplitude, just put the value and get the answer. What is bulk modulus given here? Sir, 1.4 into 10 raised to power 5. What is value of k? That k is nothing but 10. What is S naught? That is the 10 micrometer. If this put value, so what will happen here? This will become 10 raised to power 6 and 10 raised to power minus 6 cancel out, and this will equal to 14 Newton per meter square. Okay, sir. What is the equation of sound wave in terms of pressure? Say this is the equation of sound wave in terms of pressure. If we put this value, this can be written as 14 sine omega, that can be written as 500t minus 10x plus pi by 2. This is our answer. I hope this is clear to every student what is basic procedure and how we can implement the given concept in the numericals. Okay, beta, actually what will happen in the wave, we just take care about the formulas, and we have to be very careful in which particular question what is our approach. Okay, so we can say that this is easy topic if we remember all the formula and how we can apply the concept in particular problem. Okay, our next is what is the wave diagram of displacement and pressure wave. What is the meaning of wave diagram? Actually, we want to do some mathematical analysis, and if we write down the equation of displacement wave, equation of sound wave in the displacement form, equation of sound wave in the pressure form. So this is the graph of sine theta. And if we say that if we want to study the equation of sound wave in the form of displacement and in form of pressure at particular time, what is that time? Say that time is t equal to 0. What is meaning of this? If we fix the time, then we want to analyze the position of sound wave. The sound wave is moving in such a way. Okay, so if we put t equal to 0 here, the equation of displacement wave is like this and the pressure wave is like this. Okay, so this is nothing but graph of sine theta. This is the simply graph of sine theta. Here we can say x equal to 0, displacement equal to 0, x equal to pi by 2, the displacement will become maximum. So what is basic interpretation of this particular graph? Let's see. We can say that if we analyze at t equal to 0 and look at the particle that lie at x equal to 0. Okay, so what we observe, beta, if we increase the x, then the displacement of particle is positive direction. If we move leftward of origin of particle, then the displacement is negative direction. What is the meaning of displacement in positive direction, in negative direction? We know that the sound wave is a longitudinal wave. This wave is only moving like this. Here we don't confuse with this graph. Particle is moving like this. No, this is just a representation. We can say that this particle which is lie at origin. So what we can say that if we move rightward of origin, the displacement is positive. It means particle moving towards the positive x-axis. And if we just see the leftward of origin, particle is moving downward, graph is moving downward. It means particle is moving leftward. So here what we can say that is the density decreases because particle is moving away from each other. And what is known as such type of localized area when particle is moving away. When particle is moving away, then density will go decreases, pressure will go decreases, and such type of localized area is known as rarefaction. Yes, yeah, no, beta. Rarefaction. Okay, sir. What is conclusion from here? Whenever displacement of particle is zero, then we can say that rarefaction occur. Rarefaction means density minimum, pressure minimum. Okay, sir. Sir, if we see at this point also we can say that displacement is zero. Yes, we can say yes, displacement is zero. So if we see just neighborhood of rightward of this particle, the displacement is negative. Oh my God! If displacement is negative, what is interpretation in the term of longitudinal wave? At this point, the particle is moving in leftward direction. The particle which lie leftward up, rightward up, this particle moving towards the particle. Okay, sir. If we observe the particle which lie leftward of this particle, having the positive displacement. What is the meaning of positive displacement? Moving toward right. If graph is upward, it means moving toward right. If graph is downward, moving towards left. This is the basic conceptualization here. So we can say if this is moving downward, it means this is moving here, leftward direction. This is moving upward, it means this is moving rightward direction. Oh my God, two particles approaching to each other. It means the gap between particles is decreases, then the density between particles is increases. The density between particles is increases. We can say that this localized area is nothing but compression. This localized area is nothing but compression. Okay, sir. So what is graph of, what is meaning of compression? Pressure maximum. Okay, let's see from the pressure diagram. The pressure equation for T equal to 0 is this one. Okay, this is nothing but graph of minus cos theta. Plus cos theta starting from +1, minus cos theta starting from -1. So if we plot the graph, this is the graph of minus cos theta. And as we feel by intuition, at rarefaction, the pressure should be minimum. Yes, this is correct. And pressure is minimum, that is minus EKX0. Where the compression is occur, pressure should be maximum. This is also correct. So we can say that whatever we feel, that is proven by the graph of the pressure wave. Okay, beta. I hope this is clear to everyone. What is the concept and how we should remember the concept. Okay. I hope this is helpful for all the students, how we can write down the equations and how we can analyze the situations also. Okay. Next is, what is the velocity of sound? Actually, in the transverse wave, if I am talking about wave on string, then the formula of the transverse wave or wave on string is written in this manner: T upon mu. What is T there, beta? T is tension in a string. What is T there? T is tension in a string and mu is mass per unit length. So whenever we want to write down the velocity of wave, the simple term is nothing but elasticity of medium divided over inertia of medium. If medium is more elastic, it means the medium want to propagate the wave, medium support in propagation of wave. So elasticity property that will help in propagation of wave, that makes faster movement of wave. Inertia of medium that causes a resistance in the propagation of the wave. So in this manner, we know that whenever I am talking about the elasticity of medium, it means we want to write down modulus of rigidity, modulus of elasticity, bulk modulus. And we already know that from the chapter of mechanical property of solid, when I am talking about liquid and gas, or liquid and gas bulk modulus is defined. They describe the elasticity of that medium, that fluid. So here elasticity of medium that can be written in B, and the density of medium is rho. Whenever I am talking about wave in solid, so here we have to write down the Young's modulus, that is the modulus of elasticity. I hope this is clear. Why I am taking B for liquid and gas and Y for solid, because liquid and gas, the elastic property is determined by their bulk modulus. Okay, beta, let's move further next. So here we generally what we observe, that is the experimental data, that Young's modulus is greater than the bulk modulus. So we can say the velocity of sound that is depend upon the elasticity of medium. So velocity of sound is greater than in solid, greater, more in liquid and gas. So this is the order that we can keep in mind. The velocity of sound in solid medium, it will become maximum, and in the gaseous medium, it will become minimum. Okay. So here there are two concepts that is given by two different scientists. One is the Newton. According to Newton, what Newton considered that, what is the convention of Newton? The sound travel in air isothermally. It means temperature is constant. It means if according to Newton, if sound wave is moving in isothermal process in the air, what is the meaning of this? In the starting of sound wave, we describe two property. One is what is the bulk modulus for isothermal process, and what is the bulk modulus for adiabatic process. And we already know that, guys, if I am talking about the bulk modulus at isothermal process, that is nothing but bulk modulus for isothermal process that can be equal to pressure of that particular medium. Okay, so here in place of B, we directly write down B here, and this is the density. So we know that in air, what is the pressure? That is generally 1 atm, and 1 atm is almost written as 10 raised to power 5 Pascal. What is the density of air? That is the 1.29. If we put this value and solve this, this will come out 280 meter per second approximately. Okay, but experimentally, what was the speed of sound in air? That is 332 meter per second. Okay, so what we conclude from the Newton's speed formula for sound, that this is differ from the actual value of sound velocity in air. And there is another scientist, that is name of the scientist is the Laplace, and Laplace they correct the given formula, and this supposes that the air is, the sound is traveling in air, not in isothermally, but adiabatically. It means the air, when sound is propagated in air, it cannot transfer any type of heat from the surrounding. Okay, so if Laplace correct this equation and some modified term that involve in this equation, and if he considered the process is adiabatic, then what we will get for velocity of sound? Let's see here. According to Laplace, that is also known as Laplace correction formula, the sound travel in air adiabatically, that is the heat transfer is zero. So here the bulk modulus for the adiabatic process we already derived and we already know in our first class, that is the gamma times P, where gamma is the adiabatic index or ratio of specific heat. What is gamma beta? That is the ratio of Cp upon Cv. Okay, sir. Generally, in air, 79% is nitrogen and nitrogen is diatomic gas. So we can say that if for air is treating like as a diatomic gas. Okay, and we know that for diatomic gas, Cp and Cv we already know, and degree of freedom of diatomic gas is 5. Okay, so what is gamma? That 1 plus 2 by F. If we put this value, this will equal to 1.4. So this is the adiabatic index for the diatomic gas, something like as air. If we put this value and one additional factor 1.4 that I introduce here, so what we will get, that approximately that closer to experimental value. So we can say that the Laplace formula is that is almost correct formula. Whatever result we already got from the experimental result, the same type of result that we will get from the Laplace correction formula. Okay. So what we have to understand here, we have to know the what is the velocity of sound in the terms of Laplace correction formula. In the place of v by rho, we have to put gamma p by. Okay, beta. Let's move. Can we also write down, because here air is always treating like as an ideal gas. Okay, and when we will discuss about ideal gas, the first thing came into our mind, that ideal gas equation, that PV equal to nRT. Everybody aware about this equation. This is known as the state equation of state. Okay, sir. Sir, if we want to write down this equation in the terms of density and pressure, how we can write down? See here, Vita. Number of mole is always written that mass upon molecular weight. Here molecular weight, that we can say that capital M. Okay. And if we multiply molecular weight in left hand side and mass upon volume, if we put together, then what we will get? Oh my God, mass upon volume is nothing but density, and pressure upon density, this can be written as RT upon molecular weight. Oh my God, this is the very important relationship we should know from kinetic theory of gases. Okay, so in place of P by rho, if we put RT upon M, then this is the again a popular formula of velocity of sound when the temperature of gas is given. And if we know the molecular weight of gas, because if gas is defined, then we can also say that we already know the molecular weight of gas. We can also find out the velocity of sound. What is the keen observation from here? Is directly proportional to under root temperature, and one thing that is also written as absolute temperature. So whenever we want to apply this formula, put the value of temperature in Kelvin, that is the meaning of absolute temperature. Okay, beta, this is very important formula, so that I will give 3-star mark. Okay, so this is the question I just taken from the given concept. Here the temperature at which the speed of sound becomes double as was at 27 degrees Celsius. We have to find out the temperature. So we can say, suppose this temperature is T, where the velocity of sound will double, that is at 27 degrees Celsius. So what is the velocity of sound at 27 degrees Celsius? That we can say gamma RT. If we convert 27 into Kelvin, this will equal to 273. That 27 plus 273, that is 300 Kelvin. Put here 300 Kelvin and say molecular mass is M. What is the temperature? Suppose this temperature is T. So again, this can be written as gamma RT upon M. If we solve the above equation, what we will get here, beta, if we squaring both the side. So gamma RT upon M, this will equal to 4 times gamma 300 upon M. Here gamma R upon M is cancel out and temperature is nothing but 1200 Kelvin. But answer is not given in the Kelvin. So we have to, in order to get the answer, we have to convert into degree Celsius. So if we subtract 273 here, so we will get the value in degree Celsius, and I hope 927 degrees Celsius is absolutely correct answer. Okay. So in such type of question that can be generally asked. One more thing, sometimes in order to save the time, we can apply this formula. Whenever temperature is given in the degree Celsius and it is less than equal to 25 degrees Celsius, then what we will develop here, beta, we will develop a direct formula. Here, there is no need to put the temperature in Kelvin, just apply this formula, but we know the limit. What is the constraint? Under which constraint we can apply this formula whenever temperature is less than equal to 25 degrees. That velocity at 0 degrees Celsius plus 0.61 into temperature, that in degrees Celsius. So here we know that the velocity at 0 degrees Celsius is the velocity of sound 332. And if you want to find out the velocity at 10 degrees Celsius, just put the value and get the answer. So we can also remember this formula. If the temperature that is less than equal to 25 degrees, we can directly get the answer. The next term, we have to apply what is the effect of temperature that we already discussed. Speed of sound that is increases. What is the effect of pressure, beta? What is the effect of pressure? Somebody, if asked to you, what is effect of pressure? See here, beta. If we write down this equation in pressure form, that is the original form, gamma P by rho. So if students see this formula carefully, and he can say that if we increase the pressure, velocity of sound is increases. Na baba na, never say this. When we work at constant temperature, and if we increase the pressure, density is also increases, because we know the equation that P equal to, we know the equation that Pm equal to rho RT. Okay, beta. So we can say P upon rho is nothing but RT upon M. If we increase the pressure, then density is also increases. So there is no overall effect. So whenever we have to justify, we have to observe the effect of pressure, we just convert into temperature form. And by converting in temperature form, we can easily say it does not depend upon the pressure. The temperature is constant, so there is no effect of pressure. Okay, beta. Another effect that we should keep in mind, humidity. Beta, in generally, we can say that the area that is near about the sea places, the humidity is high, because air will get more and more moisture. And what happened in the moisture? If I am talking about moisture, that in moisture, water vapor present. And water vapor, generally water is H2O. And if I am talking about what is the, this is nothing but, sir, 18. And if air is dry, then mostly nitrogen is present. And what is molecular weight of nitrogen? That is the 28. So 28 is greater than 18. So we can say that the density of dry air is more than density of moisture, because of the funda of molecular weight, right? So here our feeling is not ready to accept this thing, because what we generally think, if air is moist, then the density of moist air is greater. No, this is our misconception, because we have to understand whenever air is dry, then the contribution of nitrogen is more, and nitrogen having more molecular weight, we can say that then the density is more in the dry air. So here the velocity is having the inverse relation with density, so we can say velocity of moist air sound in moist air is greater than velocity of sound in dry air. So generally we can have what happen in the rainy season. If we can say that if we produce the sound, it is just having more and more velocity. Okay, this is the effect of the humidity in the velocity of sound. Okay, beta. So our next topic that we will discuss in tomorrow class, that is the concept of organ pipe, how organ pipe will work, and how many types of organ pipe, and what is the harmonic, and what is the resonance phenomena. So I hope till the sound 1 and 2 lecture that is crystal clear to you guys. Okay, beta. Okay, beta. Thank you so much for attending the class. Now I am going to quit the class. Okay, beta. Now, okay, no problem, beta. Okay.